Hello, we're going to get started on 4.7. Bear with me as I pulled it up. And here we are. So 4.7 is a continuation of our kind of rational equation conversation from 4.6. And this time we're going to talk a lot more about just solving rational functions and rational equations. Let me get this screen together. There we are. So the first example is just jumping right in. Let's solve rational equations symbolically. I actually don't know why it keeps doing this to me. All right, so we're going to solve this equation symbolically. The way we're going to do this is basically, like we said in 4.6, we could set this up as a ratio. So one option is to say 3x over 2 minus x equals 5 over 1. By cross multiply, we get 3x times 1 is 3x equals 5 times 2 minus x. Now, when you multiply by variables, you do run the risk of having extraneous solutions, so we will have to check our work in the end. But right now, we can just distribute the 5, and we end up with this statement, 3x equals 10 minus 5x. Add 5x to both sides, and we get 8x equals 10, and divide by 8, and that is x equals 10 over 8, which reduces to 5 over 4. Okay, so 5/4 would be our answer. Let's see how the textbook does this same question. Oh, first, I didn't even mention this. We do need to identify the domain because the domain will tell us if our answer is going to be like in the domain or if it's a restriction. So the denominator cannot be 0. So we say 2 minus x cannot be 0. And we solve for this by adding x to both sides. We get 2 cannot equal x, or x cannot equal 2. So that's a restriction. X can be anything except for 2. So when ours is 5 over 4, that's 1.25. That's not 2. So we should be fine with that as a solution. So the way the text does it is that they multiply by the denominator on both sides, and then they still end up with the same resultant that we did. So really you can do it either way. You can multiply by the denominator on both sides, or you can set up a proportion and cross multiply. Okay. In doing that, you do get to the exact same result. And that is that x equals 5 over 4. And x equals 5 over 4 is a part of our domain, because remember, the only restriction is that x can't be 2. And so we're good. Okay. So they're just showing us now this kind of cross multiply method. So the solution, we say, is 5 over 4. So we need to check our work. And the way you check it is you just substitute that value in for x and say, does this really equal? And so when we multiply 3 times 5 over 4, we get 15 over 4. And 2 minus 5 over 4 is 3 over 4. Remember that 2 can be rewritten as 2 over 1. And when you multiply by 4 on both the top and bottom, we get 8 over 4 is the same thing as 2. So 8 over 4 minus 5 over 4. That's how they got the 3 over 4. Okay. And then when you're dividing fractions, you have 15 over 4 divided by 3 over 4. Remember, dividing fractions is the same as multiplying by the reciprocal. So this is times 4 over 3. The 4's cancel, and you end up with 15 over 3, and that is 5. So when it says, does it equal 5? The answer is yes, it does equal 5. If we graph this equation, we're going to graph the left side first and then the right side. And you want to find out where they equivalent. They touch right here. And that's 1.25 or 5/4. So that is our X value. We're going to do another example, example 2. In this case, we can't just set up this cross multiply and divide situation unless we do some extra work. So we do need to find the domain first. The only thing X can't be is 0, because if X is 0, then our denominator is 0, and we don't want that to be the case. So we do need to eliminate those fractions. So if we were to do that, you probably remember this method a long time ago, we talked about it, but to get rid of the fraction, you multiply by the greatest common factor than all of them. So multiply everything we have here by X squared. When you do that, you basically have 6 over X squared minus 3 equals 3 over X. If I multiply everything by X squared, then these X squareds cancel, and we're left with 6 here. This becomes 3X squared. And then one of the X's will cancel. So we'll be left with 3X over here. Okay. If you need to see this in expanded form, then this would have been 3 over X times XX. And you cancel one of them, and that's how you're left with 3X. Okay. And so once you have gotten rid of your fraction, once you have gotten rid of your fraction, then you can actually keep going and just solve this equation using the methods that you have in your toolkit. So moving everything to one side, we see that this is a quadratic, 3X squared plus 3X minus 6. And we know to solve that, there's a bunch of different tools that we can use, but one of the easiest ones is the quadratic formula. But you could also just factor out a 3 and solve this by factoring. Okay, so obviously you could have used the quadratic formula here. A equals 3, B equals 3, C equals -6. Or you can say, hey, all of them have a 3 in common. Let's take a 3 out. Once you get that 3 out, you're left with X squared plus X minus 2. And so you're looking for two numbers that multiply equal -2, but add to equal 1. So that would be 2 and -1. 2 minus 1 is 1. And 2 times -1 is -2. So that works. So that's where we get these two factors, X plus 2 and X minus 1. So then you set those equal to each other. I'm sorry, to equal 0. And you get X plus 2 equals 0 or X minus 1 equals 0. So it's X equals -2 or X equals +1. And those are your solutions. And the domain, remember, X just couldn't be 0. So neither of those are 0, so that works. Remember, cross multiplying is only an option when you have single fraction equals a single fraction. Okay, and so then we just check our work by substituting the values in. So check -2 first, and you'll see that they do equal. Then check 1, and you see that they do equal again. So that works. Verifying it on a graph. If we were to graph the left side and the right side, we want to know where they touch. So here at -2 and here at 1. So that is where we call those solutions, where the graphs touch each other. All right, let's do another example. Solve this rational equation symbolically. So now we have fraction plus a fraction equals a fraction. And I would say the first step for me would be to solve this by getting a common denominator, right? So in this first fraction, I probably want to multiply this guy by X minus 1. X minus 4. So let me write it out. We have X plus 4 on here. I would multiply this entire fraction by X minus 4. Remember, if you do it on the top and bottom, you're not changing the fraction really. Then we have x minus 4 as a denominator here. So we're going to multiply this fraction by x plus 4. This fraction we don't have to multiply by anything because x squared minus 16 is x plus 4 times x minus 4. You can double check that. X and x squared minus 4x plus 4x, that makes 0 x's in the middle. And then negative 4 and positive 4 make negative 16. So basically we would have the same denominator across the board. Once you have the same denominator, you can like disregard the denominator. And so on the top of this first fraction, you'll have x minus 4 times 1 plus 1 times x plus 4 equaling 8. And that's all we have to focus on because our denominator is the same across the board. So then we get x minus 4 plus x plus 4. And that's going to give us 2x. And then that's it. Because minus 4 plus 4, that makes 0 equals 8. So divide by 2, x equals 4. That is the answer. But we need to pause the video right now and see if that makes sense to you. If it doesn't, I'm about to show you the way the textbook does it. So. Eraser is definitely a slower process than I thought it would be. That's okay. So the domain x can't be 4 or negative 4 because that would make the denominator 0. You're going to write that first fraction as factors, which is x plus 4, x minus 4. We're going to eliminate this by having the same fraction in the denominator. So that's what we did. We multiplied both sides by that denominator, basically. And you can see all the things that cancel out. So we're good with that. And we solve this equation and we get 2x equals 8, so x equals 4. The problem here is that if x is actually 4, then the denominator is going to be 0 on the left-hand side, on the right-hand side. Because if you put 4, you get 4 squared is 16, 16 minus 16 is 0. You can never have 0 in the denominator. So 4 is what we call an extraneous solution. Therefore, the answer to this would be there's no solution. Because the solution that we did get is a part of the restricted domain. So therefore, there is no solution. Okay. Now let's do example 4 where we're going to apply this to like an actual application problem. So recall that y varies directly with x. If there exists a non-zero number k such that y equals kx. We talked about this right after we talked about linear functions. So k is very much so just the slope. And this thing goes through the origin. There is no y-intercept. The y-intercept is 0 rather. You also know that y varies directly with the nth power of x. If there's a if there exists a non-zero number k such that y equals kx to the nth power. So example 4 says the volume of a cylinder with a fixed height is directly proportional to the square of the radius. So volume is equal to k, like the fixed height, and the radius squared. If a cylinder has a radius of 10, and it has a volume of 200, then what's the volume of a cylinder with the same height and the radius of 5? So we first have to realize we're dealing with this direct proportionality, and we have to find our k value. So this is saying volume equals k times r squared. That's what that first statement says. The volume is directly proportional to the radius squared. So we have V equals K R squared. And we got that from that first sentence. Then we have some values. So it says the radius of 10 has a volume of 200. So V equals 200, radius equals 10. Let's find our K. So 10 squared is 100. If you divide by 100 on both sides, we get K equals 2. So now we can write our equation knowing our K. So we'll say V equals K R squared. And then they tell us, well, what's the volume if the radius is 5? So we put 5 in for R, we put 2 in for K, and we solve. 2 times 5 squared. 5 squared is 25. 2 times 5, 25 is 50. The volume would be 50 if the radius is 5. Again, this is a direct proportionality problem. And this is pretty much the same problems that we've been doing since the first unit. Okay. Then they give us kind of this like, what if? What if you needed to find the radius when you knew the volume was 50? So you'd put 50 in for V, you'd put 2 in for K, and you'd solve backwards. So you end up dividing by 2 and taking the square root. But only positive 5 makes sense, because how could you have negative 5 as a radius, as a length measurement? Okay. Here's another example, but this time we're going to be talking about inverse variation, where we have y equals k over x to the n. So it says inverse variation occurs when measuring the intensity of light. If we increase our distance from a light bulb, the intensity of the light decreases. So if you increase your distance away, you get further and further away, the intensity of the light decreases. Makes sense. The intensity, we're going to call that L or I, is inversely proportional to the second power of the distance. Okay. So if we wrote this in an equation, we'd have L equals K over D squared. All right. At a distance of 3 meters, so D is 3, a 1,000 watt light bulb produces the intensity of 0.88 watts per square meter. So intensity is 0.88 and the distance is D equals 3. We need to find K. So we're going to multiply both sides by 3 squared, which is 9. And we'll figure out our K value, which is 7.92. So now we can write a new equation, and we'd say I equals 7.92 divided by D squared. So we need to determine the intensity at a distance of 2 meters. So we'll plug in 2 for D, and we'll have 7.92 as our K. 7.92 divided by 2 squared, which is 4, gives us 1.98. The intensity at 2 meters is 1.98 watts per square meter. Of course, we're going to play this what if game. What if they told us the intensity and ask us to then find the distance? Plug in what you know. So the 1.98 equals 7.92 divided by D squared. And if you multiply both sides by D squared, then you can end up dividing by 1.98 and getting the D equals 4, and then taking the square root of 4. And only the 2 makes sense because we're talking about a distance again, and distances are only positive measurements. Last example, example 6, the weight of a fiddler crab is directly proportional to the 1.25 power of the weight of its claws. Directly proportional. So I can say W equals, we're going to call it B, sorry, the body weight. Okay. So we're going to say B equals K times the weight of the claw, that's C, to the 1.25 power. A crab with a body weight of 1.9 grams has claws weighing 1.1 gram. We need to find K. So for our B, we're going to put in 1.9, and for C, we're going to put in 1.1, and we're going to solve for K. So 1.1 times, so the 1.25 power is what we're going to be dividing by, and K is 1.69 approximately. Once we have our K value, we now have a new equation, and now they're giving us claw weight C of 0.75 grams. So we're going to plug those things in. Our K is 1.69 and our claws are 0.75 grams, still to the 1.25 power because that's the direct proportionality power. And we can solve for B, the weight of the body weight of the fiddler crab, which is 1.18. We could play the what if game, but we didn't. Oh my goodness, there was one more example and I didn't even know. Okay, suppose that a construction zone can allow 50 cars per hour to pass through. We talked about this in 4.6. And that cars arrive randomly at a rate of X cars per hour. Then the average number of cars waiting in line can be demonstrated by this function. Okay. Last class, we evaluated N of 40 and we interpreted the results. So N of 40 was 3.2, and that meant that about 3 cars were waiting in line if 40 cars were arriving every hour. This time, we're going to approximate, well, when is there only 2 cars? N of X equal 2. So we don't know how many cars are arriving. That's the question. So we're going to set this guy equal to 2 and we're going to solve backwards. You could set up a cross multiply and divide situation, but you're setting it equal to 2 because this entire function tells us how many cars are waiting. So when they said N of X equal 2, that's telling us that 2 cars are waiting. So we're going to solve this equation. We're going to put it all on one side and we see our quadratic. We're looking for 2 numbers that multiply to equal 5,000, negative 5,000, and add to equal 100. But those are gigantic numbers, so the quadratic formula could come in handy. Substituting your A, B, and C into the quadratic formula, you'll get the square root of 30,000, which is about 1.73. I'm sorry, the square root of 30,000 is about 1.73. So when you do that in the calculator, you get that X is either 37 or negative 137. Well, what's negative 137 cars coming an hour? So that part doesn't make sense. The only answer would be 37. So if 2 cars are waiting in line, then that means about 37 cars are arriving randomly in that hour. The whole point in this is, do you know how to solve rational equations? The first thing you have to do is learn how to set them up. So we're setting this guy up to be equal to 2 because we know that if it says N of X equals 2, then we can take this whole equation and set it equal to 2. And that's it. All right, thanks for watching.